Okay guys, so today we're going to talk about logistic regression for binary classification and how it works, and even talk about the loss function, the error function. So first of all, let's look at logistic regression, and let's first understand what binary classification is. So basically, classification, what is classification? First of all, classification is for classifying something, obviously, classifying with a label. And for binary classification specifically, the label is going to be 0 or 1. And how do we get the 0 or 1? We get that from a logistic function, from logistic regression. And that's how we get the 0 or 1. We're classifying something with 0 or 1, and we use training data to get that. So I think it's pretty obvious then, classification. And one example is like that I'm going to use a lot in the video is about like if you have a patient and you're given their height and their weight and their blood pressure, you want to predict their health. So a good health might be 0 and a bad health might be 1. So that's just an example. Or first, let's define what the function is. So think about what function gives us a range of 0 to 1 exclusive. What type of function, for example? Just pause the video first and think about it. But basically, we want a range from 0 to 1, and it has to be exclusive because we're going to use a threshold to choose it. I won't talk about that. So, a function that was like f of x equals to 1 over x if x is greater than 1. Given that x is greater than 1 as its domain, this range will be between 0 and 1, right? It is. You can even test it yourself. It's going to be between 0 and 1, the range. And it's going to be exclusive. The problem is that it's not really that special. It doesn't give us like a good shape. And if we want a shape that looks like this, you might be thinking why we want that special shape that goes from 0 to 1 is restricted at 0 and goes to 1. So it will be like something like this. And these are like, it's like 0 here and there's 1 there, but it's not really inclusive there. And here is like the middle where it could be anything in between. And these are what we use for the probabilities. If something right here, for example, 0.75, that would be close to 1. If we set a threshold, we will set a threshold there at 0.5. If it's greater than 0.5, it's going to be probable. If it's not, then it's going to be non-probable. So here it would be probable and here it would be not. And then maybe if it's 0.5, then it's going to be inconclusive. And we might have to try again, but something like that. And what function makes this? There's a special function, and it's called the Sigmoid Function, which is a logistic function and has the Greek letter sigma, lowercase. And this is equal to 1 over 1 plus Euler's constant e to the power of negative z. It takes in z. Okay, it doesn't take in x. It's kind of similar, right? 1 over something. This is 1 over e to the negative z. But what is z? This is also, by the way, this is how it looks like right there. It's special for that reason, and also because it has Euler's constant. But what is z equal to? And z is not actually just something that's just a domain. It's actually a linear combination. That's special, right? A linear combination, and you might not know what that is at all. Ax plus by equals to c. That's something you've seen here a lot in your algebra class. Ax plus by equals to c. This is a linear combination right here. Because if it's all linear, a non-linear combination would be something like this. Ax squared plus bx plus c equals to 0. This is a quadratic and it's not linear because of these x squares here. So this is what a linear combination is. It's not that bad. But it's also defined formally in linear algebra as a dot product. And a dot product for z, the dot product is just equal to xi. And I'll explain what that is. Dot for dot product, dot beta. And I'll explain what this means also, because it's nobody even knows without even explaining the context. So what is xi? the input features for a specific data point, the ith data point, and beta is just the parameters. A vector, and this is also a vector. And this comes from the X matrix, which I'll talk about as well. So first of all, let me define what this is also. The linear combination, because this doesn't look linear right now. It doesn't look like anything you recognized. So I'll explain. It's a dot product, which a dot product is really the sum of all the components multiplied of each vector. These are you can only take dot products of vectors. You can't have a dot product of a matrix and a matrix, or a matrix and a vector. Those are different. So that's why you can take a dot product here. And k equals to 1. Let's say k instead of I, because I is already in the xi vector, to n, because there's n components in each one. And it's really just going to be xi, k, that's a little bit confusing, but I'll explain that, times, just times, not dot product, just times beta of k. That's what it is. Xi k, beta of k. This is like a double subscript, I guess. Let me go and write it in a better order, because it will look more pleasing to the eye if I write it like this. Beta times xi dot xi, and we'll just write it as beta k times xik. Now it's not a dot product anymore because it became a dot product in there. Yeah, we had dot product code, dot product. And now, what this is defined as, the sum of this multiplication, which is all the components inside of these two vectors, it's just going to be beta naught, but beta is going to start at, it's going to be really, because beta naught is a intercept, there's actually intercept in there, so there has to be another thing, I forgot to introduce that. Beta naught plus this dot product, that's what z is. So z is equal to that plus beta naught. And what beta naught is just the intercept. And if all the components of x are 0, xi are 0, then that means that we're going to assume beta naught as the parameter. And I'll talk about that more, because that doesn't make sense right now, right? So beta naught plus beta 1 times xi of 1 plus beta 2 times xi of 2 plus beta naught, beta 3 times xi of 3, and I'm just going to keep going because I don't want to write it forever, plus beta n plus xi n, where xi is a vector, though. Remember that xi is a vector itself. So, and this is also not making sense, right? So I'll explain this a lot, and I'll try to make you understand this, okay? So what is xi, first of all? Xi is the input feature, a specific data point for the input features. This is what z is. Beta itself is a vector. Let me talk about what this is. So first, we know this already, so I'm not gonna, I'll show this later again, because if I have to get space for talking about beta. Beta is a vector. It's just beta naught. It's sometimes included, but I'm just gonna think of it as an intercept, so let me not include that. So let me just make it beta 1 plus beta 2, and then beta 2, and then beta 3. And this is just a vector with 3 components. For example, we're taking 3. Let's say we have 3 features. Okay, and I don't want to write n again like this. So let's say we have 3 features. Then I'm going to rewrite this up to I3. And we're going to go up to 3 here. Just for simplicity, and also because I'm going to have an example. So this is all just constants inside, scalars inside, just components of the beta vector. And you should know what a vector is. It's just like a list in Python, or an array. Xi is equal to xi1, xi2, and xi3. That's what xi is equal to. And xi is part of a matrix. And I gotta explain what a matrix is also. This is what they are, just what these are. And you're just multiplying this by each one. You can see we're just adding all of those times each of the components. So xi1 might be a specific feature, xi2 might be another specific feature, and xi3 might be another specific feature. So we can say, for example, for our example, we're going to consider that xi1 is the height of a person, of a patient. This is just the ith data point, okay? Any data point we have. And now xi2 is going to be the weight of the person, of the patient, and xi3 will be the blood pressure of the patient. Not too much data, we're going to keep 3 for simplicity, and these are all constants that are random at first and then adjusted so then they can affect these input features. These are input features. Let me write that here. These are all input features. These beta parameters, they affect, you can see here even these multiplying them, they affect these input features in the right proportion. So it affects Z, and that affects the sigmoid function, and that affects the output. Okay, it affects the output as well. So I'll go and explain this. So we know that if we, for example, let's take beta naught out of the picture and think about, or let me just keep it in there. Let's say beta 1 was equal to, for example, okay, and we have a scale of 0 to 1. So beta 1 is equal to 0.1. Let's say beta naught is equal to 0.3. Beta 1 is equal to 0.1. Beta 2 is equal to 0. Let's see, we have, this is going to be 0.4. Let's write it 0.2, and beta 3 is going to be, this is 0.3, 0.3, so that's going to be 0.6. So then we can write this as 0.4. And consider that 1 means unhealthy, and 0 means healthy. Okay, we're going to consider this just an example. For our example, we're going to consider that. So that means that beta naught is kind of contributing to it. I think I shouldn't have it that high. I can change it with beta 2. It's a little bit too high, so that's beta 2. It would be 0.3, right? Because 0.2, that would be 0.3, 0.3, yeah. So beta naught is really not contributing too much. It is kind of. Beta 1 is not really contributing at all. Beta 2 is kind of contributing, and beta 3 is contributing the most. So that means blood pressure is not that good for the patient, probably. And that means that the weight is kind of bad also for the patient. Now, we can see even that if we multiply it, if we, for example, we take beta 3 and we multiply it by xi3, that will be 0.4 times the blood pressure. So that means the blood pressure weighs more in the calculation of the linear combination, and that also weighs into the sigmoid function that gives us the output. Okay, I hope that helped you a little bit at least. Now let's talk about what is the X matrix, so you understand that, because that's very important, because this might look like very confusing, but it's really just the ith data point. We already know that sigmoid of Z is equal to 1 over 1 plus e to the negative z. So I'm going to keep that in there for now. Let's go see data first, okay? Let's say we had we were inside of an Excel sheet, our CSV file, and we were looking at all the data. We had the height, and we had the weight, and we had the blood pressure. Okay, we had all of these. So we have all of these. Let's look at only one data point, for example, or two. Let's say the height was 154 centimeters. The weight was is like 113 pounds. Blood pressure is like 76 whatever unit they use for blood pressure. But this is gonna be let's say this is the first data point, and we have a second data point as 172, 136, and then the blood pressure is 84. And then we have the third data point with, let's say it's 125, so that, and weight is 105 pounds, and then the blood pressure is 79. And then now we can have a label for each one. We can make a label, and let's say this label for this is healthy, so it will be 0. Let's say this was unhealthy, so it will be 1, and this was, let's say this was healthy, so we say 0. So we have 0, 1, and 0. These are our labels that we defined. These labels we defined ourselves. So what we call these labels, our own defined labels, we call them y. I though, because for ith label, any label, it's going to be y, but I'll just call it y for now. And a specific label is yi. Okay, these are all our labels that the actual labels we give and we define for the model to learn. That's why it's very important to actually have the correct labels. This might not be correct because I'm not a health expert, but for data science scientists, they do this. Now we know this. Okay, this is very simple. It should be very simple to understand. Now when we have the X matrix, though, we're going to collect all these values. And we can also notice this first data point. We can call it x1, and we can call the second data point x2, and the third data point x3. So we can define the X matrix as a collection of those data points, x1, x2, x3. Right there, we just collected all of them. And this is really a matrix here. These all are vectors. These are vectors, and a collection of vectors is a matrix. Okay, so now we can go and rewrite this as x equals 2. What that is, which is 154. We can just write all the numbers in here. 172, 125, 113, 136, 105, 76, 84, and 79. And this is what the matrix is for the data points. This is x1 here. This is x2. And this is x3. So we have 3 data points. And that's what xi means then. Xi means it's any ith data point. So if we consider I equals 2, it will be x2. That's why we're having that, and we have these features. So this is the height, h, and this is the weight, w, and this is the blood pressure, b. Okay, and we can even see here that these are itself, these are like vectors itself. The w vector, h vector, the blood pressure vector, all of these are vectors itself. It's like a lot of stuff going on, right? So you can see that. And that's what we can also use to our advantage to understand that's how we can understand z from that. That's how we can understand z more from that. So first, let me go erase things. And this should be clear, okay? Now we can redefine how it is. You can redefine what z is and also x. What we can do for z. We can see that, and this could be like h1. This could be h1, w1, b1, h2, w2, b2, h3, w3, b3, all for these vectors. Okay, for the data points. So we can now write this, like if we have z, now if we have z as x, as the matrix times the parameters. Now it's times, it's not dot product anymore because we're not multiplying two vectors. So it's not a dot product. Now it's matrix vector multiplication. You'll hear that a lot. That's what this is. And we're now going to consider h1, w1, and b1, and h2, w2, and b2, h3, w3, and b3 for any, because we can have any numbers. This is just what, for example. And then we have beta 1, beta 2, beta 3. See that? Now we see this, and you can see this is just x times the matrix x times the beta vector matrix vector multiplication. And we see this is h, this is like the h vector, and this is the w vector, and this is the blood pressure vector. And we can go and simplify this actually, and we can multiply them out. So z will be equal to it's b will b naught. We have to write b naught in the beginning. Forgot to write that for the intercept. Beta naught plus that. So we gotta write beta naught. I forgot to write beta naught, guys. So remember, you write down beta naught. So beta naught plus beta 1. This is a linear transformation, so you can actually multiply it like this. Beta 1 times h1, h2, h3 plus beta 2 times w1, w2, w3 plus beta 3, and then we have b1, b2, and b3, all of these. And we can simplify this again. And I gotta go and erase this now. But that should make some sense, and I'll go and explain what the linear transformation is. Just when you apply this, just the linear transformation, the multiplication. You just apply this linear transformation to the matrix. You just apply AX, and to this, you just apply AX hat plus BY hat plus CK hat. And we have that, keep going like that. This is just the linear transformation we use for multiplying them. And you can see that beta 1, beta 2, beta 3, these are all just constants inside. They're just components. And x hat, y hat, and k hat are not, they're just unit vectors. Okay, just consider that for mathematical terms. But now we can rewrite this. This might be very unorganized. I'll put it up there. And now we can rewrite this as z equals to b naught plus, we know this is the h vector, plus b1 h plus b2 w plus b3 b for the blood pressure, weight, and the height. Another thing that you can tell is that when you had this x1, x2, and x3, and when you had xi's, when you had all the xi's, like xy, i1, xi1, let's say we had xi1, that would just be, that would be hi, because it would be hi actually. So if we're choosing, because of xi1, if we're choosing any of these, it could be I could be any one of these. So if I was equal to 1, for example, if I was equal to 1, if I was 1, then it would be x11, not x11, it would be x11, and that would be h of 1, because of x1 would just be this, and the corresponding feature is the first feature. We're looking at the first feature, that's 154, and that's h1. This is h1 here, and we know that from this h1, so that would just be h1. So this is why this is true, and you can even see xi2 would be equal to, that would be just be w of I. We can do the same thing for xi3, that would just be b of I. See, isn't it interesting how that works? And you can see now, we had the previous z expression, we defined it as z equals to, previously, let me write previously, I had to erase everything because it was kind of getting too convoluted there. Previously we had beta naught plus beta 1 times xi1 plus beta 2 times xi2 plus beta 3 times xi3, and we already know that now xi1 is just h, and xi2 is just w, and xi3 is just b, the blood pressure. So we already know that, and that's what we just did here, and we just used the matrix itself here to define it like this. So this is another way to define z, and we know that we can connect it that way, and it always will work, right? And I can show you another thing, because we're considering the entire vector. We know that right here z is a vector plus a constant intercept. So that's what z is. But what if we choose a specific z? Like, let's say we have zi. Yeah, it's gonna be a specific data point. It would just be beta naught plus beta 1 times hi plus beta 2 times wi plus beta 3 times bi. Okay, this is what it is, and that's just what an ith linear combination of z, which is z, the ith linear combination that we input into the sigmoid function, which would just become this now. If we just input it to this, it would just be equal to, it would just be 1 over 1 plus e to the negative zi. And this also has another name that we call it, which is y hat or they don't use a capital, I don't think. It's called y hat I, and this is our predicted outcome. Okay, this is the predicted outcome, y hat I, and this is what the model predicts from the sigmoid function. So we know that this is the i's actual label, yi is the i's actual label, and y hat I is the predicted outcome from our model, which is predicting from the sigmoid function. Okay, that should be clear. This is predicting from the sigmoid function. So now we can rewrite it. We can rewrite everything. I'll talk about the next thing, which is probabilities. So first of all, what is the probability? If we talk about the probability, and our model has to predict something, we want our model to predict the label. Okay, that's how we train the model. We want it to predict the label. So it's going to be the probability of yi equals to something like 1. For our example, let's think about 1 first. Given the beta parameters, this means given that, this symbol here, so don't get confused about that, but it's just given that we have the beta parameters, xi, which is the ith data points in the X matrix, and this is equal to sigmoid of z. Because sigmoid of z is actually our probability. It gives us the probability that we have, and this is just y hat of I. This is just what it is. It's not too much. Oh yeah, zi. It's zi because this is a specific data point. I always have to write I too much, but whatever. And then y hat of I. So this is what it is. And if we try to do the opposite, which is the probability of y I equals to 0, given the beta parameters and xi, it's just going to be the opposite of this. So if sigmoid of zi is equal to 0.7, the opposite of that, opposite probability would be 0.3, right? So that's 1 minus 0.7, which is 1 minus sigmoid of zi. Okay, that's what it is. And this is also 1 minus y hat of I. Not too confusing, right? It should make sense what this is. So now we know what this is, so we can talk about the loss function or the error function. And the error function is what we use to actually make this beta parameters actually optimized, or like go in the right proportion when you multiply it by xi, like xi1, xi2, which is just the specific features of the ith data point. Okay, so that's what we use the loss function for. The error function is called the loss or the cost function. They have a lot of names. Loss or cost or error function. What does this do? I'll talk about it now. It is a measurement, basically a measurement. It's basically a measurement of the error of our predicted value, y hat I. For our predicted value, when we compare it to the actual label. Okay? Should be straightforward. yi is the actual label, and y hat I is our predicted outcome. And you can see that here. Next, we'll talk about the actual error function that we're going to use for doing this. And then I think that's going to be all for what we're doing, because this is basically the mathematical foundation. Okay, guys, now it's time to talk about one of the most important loss functions in machine learning, or error functions, loss functions, whatever you call it. Is very important because it's used in a lot of classification problems. That's why I'm covering it. And it's the log likelihood function. And I'll discuss about it later, the convention used for it. But now I'll talk about how you derive it and how exactly it works in every detail about it. I want to make sure you understand it's even used in large language models, because of large language models are really a classification problem themselves. And I might talk about that in future videos. But we got to first understand what it is. And I'll just say it's basic. What it is not that hard to understand. It's just the log of the likelihood function. What it has is weird L of the beta parameters. It takes in those parameters. And this is what it is. That's it. We could end this now. We're done. I'm joking. We're not done. This is very vague. So that's why we're not done. Okay? We have to define what this likelihood function is. And the likelihood function is also very complex. The log is not complex. I think we all know what log is, but we don't know the likelihood function. So that's why we're going to go and define it. But first, we got to understand what we're doing. And before, I was a little bit loose about notation. Now I got to be serious about it, because we're actually going to be comparing labels and predictions. So the label, the actual label, is denoted as y, which is the outcome, the output, the actual label. And for our example, usually it's going to be n labels. So that means there's going to be n number of y's. And they write that as yi, for y for index. We already know. We should know that notation, yi. And for our example, we have 3 data points. So it's going to be y1, y2, and y3. We have 3 y's. This is the actual label. Also know this is a specific label. It's not just like all the labels together. That's what y is. And we also know that y hat I, or y hat, is the prediction. Always when you see a hat, it's going to be a prediction. And now we're talking about any of the predictions with I, but it's going to be y hat 1, y hat 2, and y hat 3, because we have 3 data points. And this is our model's prediction, which is the predicted outcome. Okay, so we know this. This is just a notation. What else do we know? So we should know that the goal of the model is to predict what the actual label is. The actual label. Now we gotta use this for the log likelihood, because what is the likelihood? We gotta understand what the likelihood means. The likelihood is defined by probability theory as multiplying all of the possible probabilities given. All the possible probabilities that are of independent events. We're assuming these events are all independent, and that's just the assumption that we make. So we know this. We understand this now, because if I gotta erase this, so we can talk about how we can generalize these two into one expression. So then we can multiply them out. Because it's not going to be clear enough without doing that. So what we can say is this. We can define this a little bit, kind of. We can define this this log likelihood given the beta parameters as multiplying all the probabilities. So that's really just the probability that y1 equals to we're only considering. We're considering now that any possible probability of y1, so equals to 1 r0, given beta and x1. This is a vector, that's a vector, and this is just a scalar, and we're multiplying it again. I don't know if it will look that good, but I'll just do this. And the probability that y2 is 1 or 0, given beta and x2. And we're going to multiply one more time for the last one, which is y3, given beta and x3. So this is just a definition of the likelihood function, but it's very vague still. We still are not satisfied with this, and machine learning papers don't write it like this. So that's why we've got to change it. And we can even simplify this even more into a product. Into just like a product notation, using product notation. We know that that this is terrible writing. We already know that this, which is the sum, which this indicates the sum. We know that this means sum. We got to take the total sum. Now we're gonna generalize the product. Now we're using product notation, which is just a capital pi, and that means the product. And I don't know, it kind of looks similar to the pi like this. This is the pi. It's kind of similar, but this is just the product, a capital pi Greek letter. And it's very similar in using the notation, just for products instead of sums. So we can write it using the product notation, capital pi, and we can start at I equals to 1, up to 3. Usually it'll be written as n because we'll have n data points in practice, but I'm just considering 3 for simplicity. And now we have the probability, write that there. Okay, and we have the probability of yi is basically just this thing here, except we're considering all the possible outcomes 0 and 1. So yi given beta and xi is just going to multiply all these out. This is just expanded form, it's just that. So now we got to go and define what this is, because that's still vague, and if we say the log of this, it's not really meaningful. So now let's go and define what that is. So we can use these 2 definitions to define this. And maybe you already guessed how we can do that using a method that we use from algebra in high school. It's just a piecewise function. So we can define it that way. And I'm going to erase this now because you should understand what it means. And let's start. So first, we're going to go and take this probability of yi equaling 0 R1 given beta and given xi. So what is this? This could be a piecewise function like this. And it equals to, remember it equals to sigmoid of z I, specific component of the z vector, if yi equals to 1. Okay, we know that. And we know the opposite is true. We know that the opposite is true if it's 1, if yi is equal to 0. So 1 minus sigmoid of zi if yi is equal to 0. So that's a good way to just generalize it. But it's still not satisfying still, because if it just looks like very messy, right? We want to still get it into one function. So we can write it here without making it look like this. So how can we do that? We've got to go and think about it again. Now, what we can notice, let me just write it down here, given beta and xi. What we notice is that about these 1 and 0s, we can just rewrite. We can write this as inclusive and inclusive. I guess a product that's inclusive and exclusive. We can basically raise this to a power like 1, and we can multiply it by the other one. 1 minus sigmoid of zi, and we can raise that to 0, and this is going to give us the same thing. This one is probably something outside of the box. You probably didn't think of it, but this is what they define it to be. They think about this in the machine learning papers, that it's going to be to the power of 1, because if this is going to be there, sorry about that. I forgot to put it. I forgot to say that it's when yi is equal to 1. When yi is equal to 1 specifically, then this is true. So this is it's going to include this, and it's going to exclude this. So it's just going to be 1 there, because to the 0th power, it's going to give it 1 and make it 1. So we can do that, and we can do that exact same thing for the probability that yi is equal to 0. I can show you here, equal to 0. Then it's going to be alternating. I mean, it's just going to reverse the order. It's going to be 0 here. It's going to be 1 here, and here it's going to 1 times 1 minus sigmoid of zi, which is also correct. We can also do that. This is the same thing. This is what we're doing actually. This is the same thing that we're doing in here. Now we're just multiplying them, and I should write it like this, because if it's not a dot product, but that's what it is. And now what we notice is that yi is right here and is equal to 0. And we notice that 0 right here is the same thing as yi. This is just yi. And we can notice that this 1 is the same thing as same thing as 1 minus yi, right? Does that magic? It's just the same thing. It's just 1 minus yi. See yi right there? That's 0. You can see right there. And 1 minus yi is right here. And we can see for the other probability, I'll go and write it down, equals to 1 given beta and x1. We can even see the same thing here, that this sigmoid of zi, if we put it to the power of 1, because we want to include this from this definition there, times 1 minus sigmoid of zi, and we want to exclude this, so it's going to be 0. And we know that this is going to be sigmoid of zi times 1, right? And we see this is the same thing as yi. And we know that this is 1 minus yi. Because 1 minus 1 is 0. So that's what we can just rewrite it as. We can just generalize it, and we can write this as yi and 1 minus yi right there. And that's the power of this piecewise function and actually multiplication. So now I'm going to erase this all because if it's too much, and I'm going to go write down what this is, and I'm just going to replace this. I'm just going to replace this with this new thing and with the 1 minus yi and the yi. And I'll make a maybe summary if you don't understand. Okay, so it wasn't too bad. I hope it wasn't too bad to look at. I think it still looks kind of scary, right? But it really is not that bad. If I showed you this in the beginning, you would be very confused and you'd ask, what is going on at all? Like, what is going on? I don't know anything. But you can see now what is going on. I hope you have a little bit of intuition at least, that this is really just the same thing as a likelihood function, what the likelihood is. Just multiplying all of the probabilities, all the possible probabilities of, this is just the probability of yi equals to 0 or 1 given beta and xi. And it's just this, what we just generalized as if yi is equal to 1, then it's going to only include this, because this is going to be 1 and that's going to be 0. And if yi is equal to 0, it's going to exclude this because that's going to be 0, and it's going to include this because 1 minus 0 is 1. So that's what it's going to be, and that's what we know from the piecewise function and from the definition I already defined earlier. And we're just taking the product. That's what the product notation is for. So that's what we're doing. It's not too bad. Now we can take the log of this, and it's not too bad as well if we take the log of it. And taking the log of it, though, requires some thinking about what logs are. And you gotta understand what log is first. So let me go and just define what, let me just give like a brief introduction to logs, and you should already know what it is, but I'll just talk about it a little bit. So usually log is base 10, they use a 10 there. And if you take log base 10 of something like log base 10 of a equals to x, what does this mean? That means that 10 to the power of x is equal to a. That's the definition of a log. And what you can do is take the log of both sides. And you can say the log of this, so you can just take log of a, and that will just tell you, because usually log base 10 is usually not written as that, it's written as log of a, so it just means that, and also what happens because of this log base 10, these bases cancel out. That's just a property from logs, so it will just be x is equal to log of a, and that's the exact same thing as this. That's just one thing, but what we have to do is know that this is a product here. And if we take the log of a product, it becomes a sum. And I can show you the reason. If we have, like, for example, because we're taking log base 10, we know this. If we take the log base 10 of something, let's say we have 10 to the power of, let's say we have a equal to 10 to the power of x, and we have b as 10 to the power of y, a times b, a product, is going to be 10 to the power of x plus y, right? That's from exponent rules. So we can say now, we can take the log of both sides, and we can say the log of ab is equal to the log of this, which is log of 10 to the power of x plus y. And we already know that log is base 10, so these cancel out, and that's really just log of AB, which is equal to x plus y. And we know that x and y are equal to, what is x and y? We can see that x is equal to, we can just take the log of both sides. Log of a is equal to log base 10, and log base 10, they cancel out, so it's just x. And log of b is the same thing, it's going to be y. And so that's what we can rewrite this as. So just a very quick proof. If you want a more, if you want like a very very in-depth one, we don't have too much time in the video, so that's why. But if you want like a very in-depth one, you can look on YouTube, which is just log of a plus log of b. And that means that a log of a product turns into a log of a sum. I mean, logging, whatever I'm talking about, a log of a product becomes a separate sum of logs. So we know that already. And I can even, let me introduce another one also before we start doing this, because it's going to get messy when we start doing that. One more property of logs is that when you take something to the, when you have a log of something to the power, it becomes a multiplication, which also from exponent rules. So we know that, let's say x is equal to log of a, and log of a is really just log 10 base 10 of a equal to x. And we know that already. This means that 10 to the power of x equals to a, and we know what x equals to already. So 10 to the power of x equals to a. We can rewrite that 10 to the power of x is equal to a, and we know what x is already. 10 to the power of log a is equal to a, and if we put this all to a power, let's say the power is b, then this would be, this because of exponent rules, this would be a multiplication. So it'd be 10 b log a, b times log a equals to a to the power of b. And now we can take the log of both sides again, and now that will be log of 10 b log a. It's a lot of writing, right? Equals to log of a to the power of b. And we already know that this, because of, we already know that log is base 10, so log base 10 of 10 is going to cancel out. And we know that b log a, and now we know that b log a equals to log of a to the power b. And you can see that log a to the power b, we know that this is an exponent there, so it just, like, you think of it as going to the front, and that's what it is. And that's just a short proof. And now we can use this, what we understand about logs, to actually simplify this. And this is going to be much easier to simplify now, to take the log of this now. So we can just do log of it, log likelihood now, actual log likelihood. And that looks terrible, but you'll write this better. The log of this is equal to the log of this whole thing. And we already know that if we take the log of a product, it's going to become a separate log of sums. Or we can just change this into a summation, which is just this. And it's going to go to 3 and start at I equals to 1. And we also know that it's going to make this, because this is also a product, you can make this a sum, a log of sums. So it's going to be log of sigmoid of zi to the power of yi plus, this is a plus, not a multiplication sign, so don't get confused. And there's also one big parentheses, because we're taking the sum of the whole thing, plus log of 1 minus sigmoid of zi to the power of 1 minus yi, all the sum of all of it. And we see here the exponents there, we can just move them to the front and make it a multiplication. And that's what we're going to do now. Sum I goes to 1 to 3. And now we can do that. So yi times log of sigmoid of zi plus the other one, we can do the same thing to that, 1 minus yi log of 1 minus sigmoid of zi. And then I gotta make sure the parentheses are good. We have that, okay, yeah. Parentheses are good, I think so. You can verify they're good. But it was a long journey. But this is a log likelihood. And we just derived it. This is a log likelihood. Usually this 3 will be replaced with n, because there's n data points usually. Or we define it. So now this is what it is. This is the log likelihood, and also this could sometimes be written like this. Another way it can be written as I equals to 1 on machine learning papers. That's why I'm saying it. And I'm going to put n for now. I'm going to go have that because it's not actually equal to that. And yi log, and instead of sigmoid of zi, we're going to consider this as y hat of I. Okay? Because this is what determines our predicted value. So we're going to consider that as y hat of I. For the machine learning papers, they're considered that 1 minus yi and log of 1 minus y hat of I. Whole thing we're taking the sum of. This is also how it's written in machine learning papers, and it's written as LL for the log likelihood, or it's written as just this. So I'm gonna write it as LL for now, for the log likelihood. And that's what it is. It's not too bad, right? It's not too bad. It's just a lot of math. That's what everything is in machine learning. Okay, it's just math and programming. Okay, so what did we actually do with this? We just took the log of the likelihood function, which I already talked about a lot, and that's what we got from this. Usually the sigmoid is sometimes written as y hat I, but I'm just gonna write it as sigmoid because we're familiar with that. And then we have this. This is what we get. This is a famous likelihood function, log likelihood. But the problem is, I hope you noticed something, or maybe you're suspicious about something, but this is the likelihood, log likelihood. It means usually we want the likelihood to be very high, right? But what we're doing, we're saying that this is an error function. We're saying that it's the error function, but the problem is, it's an error function, but the problem is that when you make it higher, it has more likelihood, but the error, that means that the error is getting higher when the likelihood is higher. Is that correct? That's not correct, right? When the likelihood is higher, the error should be lower. So this has to be negative. So it's called negative log likelihood, and then we have a negative sign. So it's just this, negative. And you can think of it as negative of everything. And that's what the negative log likelihood is the real error function. So when you decrease this negative log likelihood, it's good. Because I can show you why. For example, if you have the log likelihood, and let's say it's 3.9, for example, that's just a random number, then the negative log likelihood will just be negative 3.9. And if you decrease this, if you increase this log likelihood, you'll be, for example, 15. That's good, right? And the same thing in here, it will be negative 15. And that's decreasing. So we're minimizing it. And here we're maximizing it. So it's the exact opposite. It's just opposite there. That's what we're doing. And that's why we define it as a negative log likelihood. And that's what it's used for. So I hope you understand what this is now. And next we're going to talk about next thing is how this is used for actually adjusting the beta parameters. And that's using gradient descent, and that's more complex. So now we should understand the basics of logistic regression. Now we have to talk about optimization and how we can actually use optimization for gradient descent in updating the parameters, which are the beta parameters. Remember that? We're going to update them like that, and we got to understand how the learning rate affects that, and then we can actually minimize that loss function, and that can make the model actually predict the right things. So that's why we're going to understand optimization first. And then we're going to maybe, we still have to understand comparing. First, we're going to understand optimization, then gradient descent, and then we'll go back to the loss function, the error function, and then we'll go to programming it. So let's see first optimization. What is the main idea of optimization? It's finding a minimum or maximum. So we either want a min or a max of a function. So if we have a function like this, remember this notation from high school? F of x is equal to something like this, like x plus 5. What is the minimum or maximum of this function? It doesn't really have any minimum or maximum because it looks like this. It's gonna go to infinity, and it's starting from negative infinity and going through infinity, so you can't even find it. This is not the function we work with though, because these are linear functions. We don't work with linear functions, and loss functions are definitely non-linear. So usually we're working with functions like this. For a simple example, we can use f of x equals to x squared. The most simple non-linear function. It looks like this. It has a vertex at 0, 0. So the mean of this function, mean of x squared, is equal to 0. Because if you look at it, at 0 is our x value is 0 and y is 0 at that value, and that's our minimum. Or what if we have a function like this, such as this thing? Let's say we have this function, there's a minimum and there's a maximum as well. But how do we actually find that? That's very confusing. How do we do it? In this example, it's like putting this in here, and this one is like upside down and flipped, and it's right there. We can easily find it here because this is a very simple function. We already know how to find the minimum and maximum, but what about this? You can't do it, and you gotta introduce another tool, and we gotta understand that in here, when we see this given, we can see here, if we draw a line to it, you can see the slope of this line is 0. Use m for slope. The slope is 0 at that point. And also, if we draw a tangent line to that, it's 0. And this is a tangent line. What a tangent line, a tangent means this, like if you have a circle or a curve, you have a line that only passes through it at one point. Okay? There shouldn't be, that's a tangent line. This is a tangent. So just keep that note. This is a tangent line. In this example, like a weird oval shape. I'm not good at drawing it. Anyways, this should make sense. You should understand that all of these points that are called critical points, all the critical points have a slope of 0. And we can see that here. We can see that even here, if we have like something like this, this is also has a critical point at 0 slope. And also right here, this has a 0 slope. M is 0. M is 0. That's crazy, right? But when you notice, for functions like y equals to mx plus b, what you notice is that m is the slope here. And the slope is just a constant, m equals to c, which is a constant. This constant does not change, but you can see here that the slope is drastically changing. It's like this, then it's like this, and then it's like this, and then it's 0, and then it goes down again, and it goes down again, and then it's 0 again, it goes up. You should understand the idea. The slope is a function. M is equal to m of x or something, whatever. This is a function. The slope is a function now. That's the main idea. Even here, the slope is a linear function. Slope is a linear function. And that feels weird, right? If you don't understand what this is at all, it should make at least a little bit of sense. If it's like hard to think of slope as a function, you understand here that this is 0, here it's 0, but here it's not 0. You can tell it's not 0 even here, you can tell it's not 0 here, but it's 0 there, so that means the slope has to be changing. It has to be changing with some rate. Okay, it has to be changing with some rate. And here it doesn't change with a rate because if it's just a line like this. So the slope is just going to be the slope of the line, which is just, if you make a slope triangle, it will be just delta y over delta x. So delta y over delta x is equal to m, which is a constant, and that's the slope. But now we got to think of that as a function itself. So that's why we got to go and introduce some new tools. It's very important for understanding machine learning. Let's think about that function again. F of x equals to x squared. Okay, we already know the minimum, so we can easily test it. But let's go and try to find the slope of this function. How do we actually find the slope of this function? Let's go and visualize it, remember? That it looks like this. It has a minimum at 0, 0. Okay, it's something like this. Okay, and these two are symmetrical because it's an even function. So you can see that. And now, let me go draw a bigger one so we can actually visualize it more. And I can draw some points, actually. So let me go draw like very big. This is like very big. And I'll draw it like right here. So first we see the slope is like is 0. Here, we can see the slope is 0 here. Then it slowly picks up and increases. And what you should know is that the slope is increasing at a constant rate there. And you see here, it's like the opposite. It's starting very high and is going like very low to 0. So you can tell the slope will be starting from negative, somewhere negative or negative infinity. And it's going to go up to positive infinity. So it's going to be something like this. Okay, that should make some sense. Because remember here, it's like very negative here. The slope is very negative. Going from negative infinity. It's going from negative infinity. And then it's going slowly to becoming less negative and less negative until it's positive. And it's 0. And then it turns around. So that's what it will be doing here. I didn't draw that well though. But it's going to be turning around. It's negative, very negative, and then it becomes positive and very positive like that. You might be doubting that it's linear. You might be challenging me and saying, I think it's not linear because the function is non-linear. Well, you're going to see, right now I'm going to show you why this function is increasing at a linear rate and why the slope is actually linear. So let's try to actually take the slope of this function. Actually, try to take the slope. So we can take 2 points, okay? We can take x1, somewhere here. We can take x1 and we can take x2. And let's say x2 is just a distance away. Let's say this distance is h away. Let's say the distance is h, okay? That's used a lot in many math textbooks. So this is just x1 plus the new distance. So this is really x2. You can think of it as x2, but you can rewrite it in terms of x1 because we know this h. And now we can see that this has a function value at x1. Let me write this as x, so then it's not too convoluted. So this is x, and it has a function value right there. This x plus h, and it has a function value as well, somewhere here, very high up. Right here and right here. We have these points. And right here will be f of x, because that's a function of this point. And here is function of that point, of x plus h, f of x plus h. We can take the slope of this line. Now we can take the slope of this, like a line. We can draw a line here. It's called a secant line. That kind of gets the behavior of this part. You can see it's almost the same as what I was drawing earlier. We can just draw that now. We can take the slope of that like that. You can see this should make some sense that these points here, I can even draw it out. X and f of x. That's our point right there. And then we have a point here, and have x plus h, and f of x plus h, which is a function of this point right here, because this is just a point there. Okay, should make sense. This is just a point, this is just a point, individual points. And we can now find the slope of this line. So let's try. This is the line we modeled. So we can actually take the slope using delta y over delta x, which is equal to y2 minus y1, x2 minus x1. This should be very familiar. It should be just review from Algebra 1. And now we can actually just plug things in. We know y2 is just f of x plus h. And we know y1 is just f of x. And we know the bottom x2 is just x plus h. And we know that x1 is just x. X minus x is going to be 0. So we can cross that out and we get f of x plus h minus f of x over h. This is what it is. This is the slope of this line here. This line is a secant line. It's the slope of a secant line. You can say that's slope of secant. Okay, this is a secant line, and if you're confused on what a secant is, remember you have a circle. This is a tangent. This is a secant. Just example. Okay, it crosses 2 points, and a tangent crosses 1 point. So what we want to do now is make it more accurate, and we want it to cross only 1 point now. So it's very accurate now. We want to make it cross 1 instead of 2. So what we can do is we can bring this point to here, and then we can make this point. It will go here, and it's going to be only 1 point in this. This line will become a tangent. You see that? It will be linear. How will we move it? We got to make h 0. H has to go to 0. It has to be what they call tending to 0 or approaching 0. Or we can actually move it using what's called a limit as h approaches 0. Of this, so we got to take it for this, because this is a slope. The limit as h approaches 0 for this function here. You can think of this now as a function itself. So then we're finding the slope of the tangent line, basically. And what this is the slope of the tangent line. The limit as h approaches 0. This is a function now, so we can't write it as only m. So that's why we write it like this, f dash of x. F dash of x. That's what they use to write this, f dash of x, and that is the slope of this function. At any point, you can actually find what the slope of the function is. This is f dash of x. The whole thing here is f dash of x. This whole thing. That's the slope of the function. Now we can go and plug it in. The limit as h approaches 0 of x squared, x plus h, which is going to be x plus h squared minus x squared over h. And if we simplify this, I'm going to write it here. The limit as h approaches 0, and we have x plus h squared. So that's going to be x squared plus 2hx plus h squared minus x squared divided by h. And this x squared is going to cancel out with that x squared. So we can factor this now. Limit as h approaches 0. I'm going to do this fast. So we have h, and we have 2x plus h. And we have h here, so we cancel those. And now h is going to be 0, so I can write it again so you can see it. 2x plus h, and we see h is going to be 0, so we can cancel this with this. Because h is going to be 0, this is going to be 0, we have evaluated the limit, and we got everything equal to 2x. The slope of the function f dash of x equals to 2x. This is the slope of this function, and it's linear. And what this is called is, f dash of x is called the derivative of f of x. This is the derivative, which is the slope at any point, instantaneous slope calculus. This is differential calculus. I just introduced it. But this is just very simple. You should understand it, even though it looks like a lot of things. It's not that hard, okay? It's very easy. If you just understand this. This is what you have to understand. You have to understand this point, approaching this point, and making a tangent line, and we're finding the slope of that. That's what the derivative is, and that's effectively just the slope of the entire function. F dash of 0 is equal to 2 times 0, which is equal to 0, and that's the slope right here. The slope right there is 0. We got it. This is what we were looking for. So we got our tool. We got our best tool, and that's called the derivative. We have f dash of x as the derivative, right? But this is not that intuitive to write, right? Why are we using a dash? We can also write it as derivative of f with respect to x, df dx, and that's equal to f dash of x, and that is equal to the derivative. That's the derivative, what it is. It's just we're taking the derivative of the function f with respect to x. And if that's also confusing, like with respect to, what does that mean? We're considering x changing. So this is what the machine learning engineers think about. So x is changing, constantly is changing, but how does f, the function, respond to that change? And we can see that if we have f of x equals 2x squared, what we just saw, we saw that df dx is equal to 2x. And if we have f of x is equal to 2x, we know that df dx will be 2, right? Because this is the slope, 2 is the slope, this is just y equals mx plus b. We know that already, and we know if we have a b here, which is constant, or let's say it's 1, it's going to still be 2, because this is the slope. And we can actually make a rule from there. We can make a rule from this. We notice this 2 here is the same as the 2 here. We notice right here when we have 2x, it's kind of hard to see. We have a 1 here, and we see we have a 1 here. It's just multiplying by 1 because that's 2 still. And we have the 2 here, and we have the 2 there. We have a 1 here, and we have a 1 here. See, we notice that we have the coefficient. If we have f of x equals to x cubed, for example now, this is going to go in the front. And we see here that this power becomes 1. So it actually reduces, it's 2 minus 1. And we can see that here also is 1 minus 1, which is 0. And it's 0 right here is just 2 to x to the 0s. And that's equal to 2 times 1, which is equal to 2. That's what it is. So we can see that 3 is going to go down. F of x equals 2, 3x. And this power is going to reduce. And it's going to be here, it's going to be 2. And we can actually write a general rule now. We can see, this is another way to write the derivative. Call this derivative of an operator. D dx is operator on the function xn. X to the power n. And what is this equal to? Remember that n becomes a coefficient, so it's nx, n minus 1. And we just saw that here in action. 2 becomes 1, and we can see 1 becomes 0. I show you right there, and we have that right here. So this is very easy now to take derivative. To have a derivative of d dx of x very easily. You already know that. You can even do this. X plus 500 is going to be still 1. Doesn't matter whatever the constant is, because we know the derivative of a constant is 0. And yeah, I can even show you if we have 0, y equals to 500. For example, y equals 500. This is just this. At 500. And what is the slope of this? This is just 0, the slope. You already know it's not changing at all, so the slope is going to be 0. So that should make intuitive sense, and this is what the derivative is. Let's go practice taking some derivatives. So I have some derivatives up on the screen. You can try to do all of these by yourself. There's just some examples. Pause the video, feel free to try it out, and try yourself. Just pause the video. Okay, now it's my turn. So I should go over these. Hopefully you can just check your answers now. So remember that this is a 5. It's a little bit confusing. It's okay. But we know that it's going to be, this is going to be equal to 5x will be equal to 5x to the 4th plus 20x to the 3rd plus 0. So it's not going to be even there. But this is what it is. derivative. Remember the rules that we just followed? And we know how the rule came from. 500 x to the 499. It's kind of weird, but I just did that to make it more confusing, but you would still do the same thing. And 18x plus 21, ignore this, because this is a constant. And now we see here as well, it's just 18x plus 5 times the derivative of this. This is just x to the power of 10. We know the exponent rule is 2 times 5 is to 10. So this is going to be x to the 10th. So this is 5 times the derivative of x to the 10th, which is 5 times 10x to the 9th, which is equal to 18x plus 50x to the 9th, which is just the final answer. Okay, that's not too bad. And this one is very easy. This is 0. We know that this one is just going to be 18x plus 100. It should be that fast. Say that we had something like this. We had the derivative applied on this function. Let's say it's x squared plus 3. And now it's getting serious because we have parentheses times ln of x. That's also a function of x. Let's first understand what the derivative of ln of x is. So ln of x, what does ln of x look like? So this is y equals to ln of x. This is what it is, the function right there. This is how it looks like. How do we find the derivative of this? You see right here at 0, it's like really steep. How can you find the derivative at 0? It's like it's a vertical line. You already know if you try to find the vertical line, it's going to be delta y over delta x. And you see delta x is 0 here, so it's going to be 0. And that's going to be undefined. So you can't even, it's not differentiable there. It's undefined, so non-differentiable right here. Not differentiable. Well, we know that it's going to be defined like somewhere right here. We know that right there, so we can find what the derivative is going to be. If you see like how it's going to be, it's going to go like this. And it's going to go like that. It's going to go like that. So the derivative has to be undefined at 0. Type of function is undefined at 0. Y over x, where x is, when x is 0 is going to be undefined. So undefined when x is equal to 0. And if we try to, now we can see this is actually the derivative. That might be very vague because I didn't actually go over it. There's also a proof on it, on how to actually find the derivative. I wanted to keep this video not too long because we have to understand trig a little bit also, because that's a little bit more important than logarithms. But this is what you should know. So we know this. So now we can find the derivative of this. That's going to be, we can't just multiply the derivatives. We have to use something called the product rule. It's a little bit unintuitive at first, but it's like this. So if you have uv, we have the derivative of u and v where they're functions. So u of x, v of x, these are product. Taking the derivative of a product, it's going to be, this example, u dash of x, v of x, plus u of x, v dash of x. This is what the product rule is. This is what it is. It's kind of looks scary. This is the derivative of u multiplying by just vx, the function. Derivative plus regular u times the derivative of v of x, which is just v dash of x. U dash of x, v of x, plus u of x, v dash of x. That's what it is. And it just looks like, why are we doing this? And there is a reason why we're doing it. And there's like a whole derivation for it also, but those are very long and it's not as important to us. We just want to understand how to use it. But what you can think about when I was thinking about it is that, remember when we had a constant like this derivative of cx to n is just equal to c times, because this n is going to multiply by c, so you can think of it as c times d dx of xn, which is equal to c n x n minus 1. That's what it is. But you can see that how this goes to the back right there. Okay, so that's what it does. You can see it went to there. It used to be in there. That's what it does. You can think of this as Now we got to think, because we have two functions. We can't just move one there because we have to take the derivative with respect to both of them. So we're going to consider both scenarios, where this one is the constant, like think of that as the constant, and now we're thinking of this as the constant. We're going to think about both scenarios and we're adding them. Just think about that as the product rule, kind of like that. But there's a whole proof for it, and I'm not going to show it because it's going to take too long. But now, I hope you memorized that already. It's okay, you don't have to memorize it. We know that, and now we can take the derivative of this first, 2x times ln of x plus, we're not taking the derivative then, and now we're taking the derivative of this, which is 1 over x, so it will be x right there. This is what the answer is. That's simple. Not that hard. We just multiply 1 over x times this, and I just put it down, like in the denominator, and we have this, 2x is just the derivative of this. We're keeping this the same. That's what the derivative is. Okay? And now let's look at a more important one of sine x. Oh no, it's getting serious now. We have the derivative of a trig function. So if we have, we know what sine x is. We have the unit circle. Okay, we have a unit circle, and we have specific values, like let's say let's see like a regular unit circle. We know this. We know we have a triangle. We know the point on the circle is xy, and x is cosine of theta, and this is sine of theta. We should know this. You know that because of this is sine theta, and this is cosine theta. This is 1. The hypotenuse is 1, just 1. And you know the sine theta is just equal to opposite over hypotenuse, and we know the opposite is just gonna be the value, whatever we call this sine length, over 1. So we can just call that sine theta, and that's what we can do the same for cosine theta. But this is why you should understand. You already know. You should know this already. This is a unit circle, sine theta and cosine theta. And if we draw this out in like a function, it's gonna be like this. We have 1 here, and we have -1, and we have let's call this x or theta, and we have pi over 2 pi. This is 90, 180. This is radians though. I'm just using radians. Pi, and then 3 pi over 2, 270, and then 2 pi. Just 360 degrees. 360 degrees, 2 pi radians. Okay, so we have a triangle. And we have theta here as an angle, and we have a hypotenuse of 1 to make it simple. Let's call this side A and this side B. Opposite over a hypotenuse, so the opposite is A, and the hypotenuse is 1, so that's equal to A, and this is just sine of theta, so that's A equals to sine of theta. And we can do the same thing for B. Adjacent for hypotenuse, that is equal to B over 1. This is just going to be B, which is equal to cosine theta. That's what we can do, and we can just write that in here. This is sine theta, this is cosine theta, and I can erase this now so you understand that. And now, if we have another angle here, this is a right angle. This is going to be 90 minus theta, right? Because of theta plus 90 plus another thing, some x, is equal to 180. Because the triangle has 180 degrees, right? So this has to be, if we find x, we can just do this. Theta plus x is equal to 90 degrees. So that means x equals to 90 minus theta. And that's what it is here. Okay, that's just showing it. I'm showing too much, but it's okay. You should understand that. So that's what it is right there. And now if we take it, this angle, 90 minus theta, it's just going to be cosine now of 90 minus theta. But now the roles have reversed. And we can do the same thing here. It's going to become sine. We take this angle, sine of that. It just becomes sine of that. We can see that cosine of theta is sine of 90 minus theta. Cosine of 90 minus theta is sine of theta. This is called a cofunction identity. And I think I showed it a bit too early, but it's okay. I just went off track, but it's okay. This is just some interesting thing about trig, and this is what it is. But let's go back to our graphic. When theta equals to 1, when theta is pi over 2, what is sine of theta? So pi over 2 is right here. that's 0, 1. We know sine theta will be 1 because this is sine theta right there, the y coordinate. So it's going to be right here. It's going to be 1. What is sine of 0? The sine of 0 right here is 1, 0. So we have sine of theta is 0. So it's just going to be 0. What is sine of pi? Sine of pi is right here. You already know that now. Negative 1, 0 is going to be 0. Again, you see that right there. What is sine of 3 pi over 2? It's going to be 0, negative 1. And you know sine is the y coordinate, so it's negative 1. And that's going to be right here. What is 2 pi? Sine of 2 pi is the same thing. It's going to be 0 anyways, so it's going to be right here. And now we can draw that out like this, like the regular call out the sine wave. Like this. This is a sine wave. And that's how it should look like. And why am I drawing it right there? That looks very confusing. Sorry about that. Let me just do it the correct way. Like this. So this is what it looks like. This is sine of theta. Y equals sine of theta. We drew it out the correct way. This is how we do it. Now we know this. We can see the slope here is 0. The slope here is dy d theta there. It's going to be 0 here because this is a critical point. It's going to be 0 here, which is another critical point. This is a max. And this is a min. Now we can see sine has a max at pi over 2 and has a minimum at 3 pi over 2. We can see that. Now if we take the derivative, what is it going to be equal to? We can see what function has a value of 0 at pi over 2, and what function has a value of 0 at 3 pi over 2, and what function is positive. You see, this is going to be a positive grade slope here from 0 to pi over 2, and has a negative. It is negative because this is a negative slope from pi over 2 to pi. What about here also? Which function also negative from pi to 3 pi over 2, and which one's positive from 3 pi over 2 to 2 pi? That's just a lot of words, right? I'm just saying a lot of things. But what is that actually? And pi over 2, what function is 0? What function? See that? And at 3 pi over 2, it's just cosine of x. And we can even see that. If I go and erase this now, I'm sorry I have to erase it. But we can see what cosine of x looks like. Similarly, this is negative 1 and this is 1. And we have cosine of theta, y equals cosine of theta here. And we have theta. Pi, 3 pi over 2 and 2 pi, okay. We got it. See, I have 0, cosine is 1. We know at pi over 2, cosine is 0. We know at pi, cosine is negative 1. We know at 3 pi over 2, cosine is 0. And we know at 2 pi, cosine is 1 again. So we can even draw that now. It's going to be like this. It's like a shift of sine. You can see it's kind of like a shift of sine. And you can see that here. You can see here it's actually, the function is positive here. Positive, and you can see here the slope is positive. And you can see here the function is negative. You can see here the slope of the function is negative. So the function is positive, function is positive, slope of the function is negative. Slope of the function, think about that. Slope of the function is negative, function is negative. But they actually call this whole thing as concaved downward. And that has a maximum. And they call this whole thing here concave upward, which has concave up, which has a minimum. Okay, so this has a minimum concave up, and this has a maximum the concave down. And you might be thinking the derivative of cosine is sine, but we have to actually see that. Is the derivative of cosine just sine? We can see if it is. So let's check now. We're going to use this cofunction identity I talked about earlier. I got ahead of myself, but whatever, it's just, there, we know this now, we should know that. And now we can actually take the derivative of cosine of x, and we can say this as actually the derivative of sine of pi over 2 minus x. Okay, because if we're using this function identity, we're going to use pi over 2, because we already know the derivative of sine is cosine. So now we can just, what I'm going to do is use the chain rule. And I didn't talk about the chain rule. and draw about the chain rule. So we have the derivative to the 7th power. Do you want to expand that? Try to expand that. You want to do it. It's gonna take all day. It's gonna take all day to expand it. So that's why we use the chain rule, and we find the derivative of the inside and multiply it by the derivative of the outside. So we use actually what's called substitution. So we make this u, and we take the derivative of that first. So what we do is dy dx is equal to derivative of u with respect to x. We take the derivative of this and substitute it value, and we multiply it by the derivative of the outside values, which is just dy du. So now we're gonna make it like u to the 7th. So now we can easily do that. That's gonna be 7u to the 6th. We can just do that, right? That's what this is, and we can see that we can cross out these u and it will be dy dx again. That's just some funny thing about the chain rule, but it's just something that shows it works, and that's what it is. So what we can do is we can say that 7u to the 6th, and we can substitute u in, which is x plus 5. And we can multiply it by du dx, which is just 1. So this is the answer. So now we can do the same thing here. We can say that this is u. The derivative of this is going to be -1, right? This is a constant, so it's going to be -1. So it's going to be -1 times sine of this, sine of u, sine the derivative of sine of u, dy ddu of sine u. So it's going to be equal to negative. This is just dy du. And that's equal to -1 times cosine of u, which is equal to -1 times, we can just make it negative now, I don't want to say that again, times again, of pi over 2 minus x. And we know that what this is, what cosine of pi over 2 minus x is, right here, it's sine of theta, or sine of x, it's sine of x in this case, negative sine of x. So this is not correct. It's not sine of x, it's negative sine of x. Okay, so now we have the actual tools like the derivative to do this optimization. Now we can actually find the minimum or the maximum. And I have a function here, 1/3 x to the power of 3 plus 5x squared plus 25x. And let's add some constant 10, for example. This is, I choose it specifically so it's easy to take the derivative and do things. So we have this function now. We can find the derivative f dash of x as x cubed, x squared, as x squared plus 10x plus 25. You can see this is very easy to factor. That's why I choose it. And now we know when we have a function like this. Let's say we want to find the minimum, and now we have a maximum as this example. dy dx is 0 here, right? We already know at this point dy dx is 0, so we gotta take this df dx or f dash of x to be 0, and that's equal to x squared plus 10x plus 25, and this is a perfect square, so it's very easy to go factor it. So 0 is equal to x plus 5 squared. We know that this is 5 squared because of 5 times 5 times 2, so it's a perfect square. We got it. We can now, we already know that x plus 5 has to be 0 by the zero product property, so x equals to -5. This is a critical point. Is it a minimum or a maximum? We can see now. How do we know if it's a minimum or a maximum? Let me draw it a bit bigger. So let's see the maximum versus a minimum example. So if this is a minimum, this is a maximum. Right here, this is a max, right? And we see a minimum is like this. Right here is a minimum, right? This is concave upward and concave downward. And this is concave up. That's what they just called it, concavity of a function. This is concave up, okay? Concave up versus concave down. And you see this has a minimum, concave up, and concave down has a maximum. The derivative is going to be like this. And right here, the derivative is going to be like this, right? It's just at one point. It's at one point. Let me just say, look at that visually. Think of it as 1 point. So with the derivative, you can see here, the derivative is decreasing. df dx is decreasing. You can see here, df dx is increasing here. It should be easy to see that, right? Decreasing derivative versus increasing derivative. That tells us that the function slope here is decreasing here. The function slope is increasing. And if the function is decreasing itself, the function is decreasing, then the derivative has to be negative. If the function is increasing, then the derivative has to be positive. And we can see that if we take the second derivative, which is the derivative of the derivative, it's going to tell us the behavior of this derivative, the slope of this derivative, this derivative was a derivative. It's going to tell us the same thing for here. It's going to tell us this derivative is negative. That's written like this. If you have d dx of df dx is equal to d squared f dx squared. That's what the second derivative is, the notation of the second derivative. So you should know that if the second derivative is less than 0, if it's less than 0, that means that this derivative actually, why did I write it like that? This derivative, the slope of this derivative is negative. Tells us the slope of this derivative is negative. That tells us the derivative, the slope of this function is decreasing. If that happens, then we know that this has a maximum. So we can tell it's a maximum. Here we have the maximum, it's decreasing there. So we have a maximum, we can tell the same thing here. If the second derivative is greater than 0, it's going to be increasing. So we have a minimum. Okay, that should make sense. But if the derivative is just constant like this, the derivative is just constant, then it's going to be equal to 0. And that tells us that there's no minimum or maximum. It tells us nothing. It's greater than 0, it's going to be a minimum. Okay? So now we know that. So now we can say, we can take the second derivative, which is going to be f dash dash of x. Now there's another dash, so that's why instead of just one dash, it's two dashes. That means the second derivative. And that's equal to 2x plus 10. 2x plus 10, this itself is a function. The second derivative is a function, so it's not greater than 0, so we can't even conclude now. So what we can say is that it's an inflection point now. So if we have this could be like derivative. Let's think of this as f dash of x. Because of f dash of x is degree 2 now, right? We see this is f dash of x because f dash of x is degree 2. It's a perfect square. That's what it looks like this. It has its own minimum. You can think of it as its own minimum. It basically has. That's what they call an inflection point. So it's when the derivative is changing from negative to positive. That means the function is going from decreasing to increasing. This is just one example. It could even be like this. It could even be like this. We don't even know what it is yet. It could even be like this, where this is going to be positive to negative. But what we can see here already from looking at this, kind of cheating, is that x plus 5 squared. We can already graph that. It's going to look like this with a translation to the left. It's going to the left 5. So it'll be something like that. The vertex is going to be a negative 5, 0. We can tell that right here. And that's basically a minimum point, the derivative. So it's going to be this example. We have actually not this example. It's going from negative to positive. That tells us the function is going from decreasing to increasing. So decreasing to increasing, that's going to be like this. So that tells us that it's going to be a minimum. Before we get into beta parameters, it might be too complex. So let's try to understand if we have a multivariable function like x. Y is equal to x squared plus y squared. Very simple, because I don't want to get it too confusing. So I have something like this. Like this. Let's say it was a circle, or let's say it was a sphere. We had a sphere, and we want to find the tangent line to the sphere. That's what we're trying to do with derivatives. Remember with this, like this, we can easily take a tangent line, right? We can just do this. Tangent line found already. Easy, easy. It's too easy to find a tangent line there. But what about when you have this? When you have a sphere, because it's 3D, it goes to 40 though. It goes up to 40, 5D, 60, ND, n number of dimensions. We have a lot of parameters. But now we have a sphere like this, and we want to find a tangent line. But there's like infinitely many directions we can go through. See, look at how many directions we have the tangent line can be in. But here it can't. We see here it can only have one direction. But now if you think this is 3D, you can go like this, you can go like that, you can go like anywhere. Too many directions. Infinitely many directions in 3D. 3D means infinitely many many tangent lines, too many tangent lines, we can't take the derivative. We have to choose a direction. We have to choose a direction. We have to. There's no other option now. We have to choose a direction. It's called directional derivatives. With directional derivatives, you can take it in a specific direction. With unit vectors and stuff, that's a little bit complex, but we don't need to do that. Usually, the simplest way is to choose an axis. An axis. We usually choose an axis, which is one direction, and we keep the other axis constant. So if we have something like this, I'm not good at drawing 3D. That's why I didn't try to draw it too much. But we have something like this, some shape like this, and this is probably not that shape. If we have something like this, and we have the x-axis, we have the z-axis. I'm terrible at drawing it though, so I'm not going to be good at it. We can take one axis constant, and we can find, we can have like a tangent line like this, and we can keep one axis constant. This is in the x direction. Okay. So what we can do is actually consider one axis, like instead of having like so many directions, let's say the x-axis was like this, so we'll have a tangent line in that x direction. So that's what we can choose. Or we can have it also in the y direction. So we can have a specific direction, not both directions, because there's infinitely many when you have both directions. So we're going to have one. And we can think of it now as one plane now. So we're considering only one plane. And it's going to be back to 2D again, right? So always we have to take it with respect to one variable. And we got to keep the other variable constant. So that's what we have to do. Remember that the limit as h approaches 0 of f of x plus h minus f of x divided by h. Remember, we just derived that. Remember this, but now we have y also. So this was f of x. Okay, that was f dash of x. But if we want to only take x constant, so now we're thinking about this sphere again, and we're now thinking about the x-axis direction. Okay, that means we're taking the what's called the partial derivative with respect to x now. So it's in the x direction, so it means it with respect to x. So they denoted as f of f sub x. I don't really like that. I like this one better, like this. It looks cooler also, but it also means more. It's like similar to the df dx, but now it becomes partial f partial x. They call it partial because we're partially taking the derivative, right? Not taking the full thing. So that's what it's equal to, this limit as h approaches 0, but now we're considering y to be constant. So f of x plus h, and now y is constant, minus f of x, y, because we have to consider y is still there, and divided by h. This is the partial derivative with respect to x. And we can also think of this as nudging the x variable. Now the x is changing. How does the function respond to that x changing? Always think of that in machine learning. So what will that be here? If we have partial, I'm not going to solve it out, it's always annoying. There's too much algebra. But now if we have partial f, partial x, for this, what is that going to be equal to? So we see this is x squared plus y squared. That's going to be 2x plus 0, right? Because y is constant. Y squared is just a constant. We're not taking it with respect to y. So it's just going to be with respect to x. So if we have the same thing like partial f, partial y, that's going to be equal to 2y, right? Let's say we are taking the partial derivative of x squared y plus e to the x y. But this is kind of important, understanding what the derivative of e to the x is. So if we have derivative of e to the x, what is that equal to? It's actually equal to e to the x. And okay, let's try it out. So we're taking the limit as h approaches 0 of e to the x plus h minus e to the x divided by h, right? That's what we're doing really, and that's equal to the limit. I'm just doing this at the top of my head. I don't even know the proof for it, so I'm just going to take an attempt. So e to the x, e to the h. We already know we can do. We can make that multiplication by exponent rules. E to the x divided by h. Divided by h. And we can now factor this is equal to the limit as h approaches 0 of e to the x, e to the h minus 1 divided by h. And now that's equal to e to the x and times the limit, because we can take this out now, the limit, because we're only taking the limit as h approaches 0. We don't care about any other variables, so e to the x has another variable. And now we can, what is it going to be, this limit, we've got to think about what this limit is. Limit as h approaches 0 of this is not going to be 0, and that's going to be 1 minus 1, that's 0 over 0, that's the indeterminate form. We can use the L'Hopital's rule for this. Let me see, limit h approaches 0 of e to the h minus 1 over h. If we differentiate with this rule, it's going to be limit h approaches 0 of e to the h of 0. Well, we're going to use the derivative again anyways. E to the h minus 0 so divided by 1, which is equal to e to the h, which is going to be equal to 1. So this is going to be 1, and that's going to be equal to e to the x, so we just proved it's e to the x. But I had to find the derivative of e to the h anyways. That's not the best proof, but I'm just showing you it could be like that, and that's what e to the x is going to be. I didn't even look up a proof, so it's going to be terrible, but whatever. So we're taking it with respect to x, so y is going to be constant, so that's going to be 2y, and x is going to be the first power, so it's 2yx. Should be intuitive, right? Because this 2 is going to go to the front, times y, because it's a constant, we can even move that to the front, times x, plus, and now e to the x is what we're taking the derivative with respect to, x. Y is a constant, so it's going to be y e to the x. So it's going to be the same thing, well, whatever. We can still write that. That's what it is, okay? And now we can even do partial y. Let's call this f. Okay, let's call that f, partial y. Now that's it. Think of that as a function notation, x, y. Okay, now let's try this, okay? So, we're taking with respect to y now. So now x squared will be the constant, so we're just going to write x squared. That's going to be the m in the mx plus b equation. Plus, and now e to the x are constant. And this is just the one variable, so it's going to be e to the x. That's what it is. And second, if we take the second partial derivative, what is that going to be? That's going to be 0, right? Like this now, same function. And we had now partial f, partial x, partial y. What is that? What does that mean? That looks weird, right? Well, it has to be a square there. That looks weird, right? Well, that's really just partial x, partial f, partial y. And what is partial f, partial y? So we can just rewrite this because we already found that. Partial x, and we know that that's x squared plus e to the x, and that is equal to 2x plus e to the x, and we find it out. Now now you try it on your own to find this. Oh, why not writing these the wrong way? Give you like a couple of seconds. Pause the video and try to find it. We have now partial y and partial f, partial x, okay? So now we're taking, it's like the second derivative, but now like mixed. It's called the mixed higher derivatives. So what is partial f, partial x? Partial f, partial x, we already find it there. Partial f, partial x, we already know that. So it's equal to partial y of 2yx plus e to the x, y, which is this partial f, partial x. That's why we can write it like that. And what is this? This is 2y, and x is just a constant. So it's going to be equal to 2x plus, and this is just a constant, plus e to the x. That's partial, that's what this is. We did it very fast. Those are examples of partial derivatives. And now let's see, actually, when we have so many of these derivatives, if we have like something very complex looking like this, and we want to find the minimum. Okay, find minimum. If we have a minimum, we're going to find the minimum of this. Do we even have a minimum first? So what we got to do is consider all the partial derivatives of this. What is that going to be? That's going to be partial f, partial x, and partial f, partial y, right? Because we have two variables. And what we do is actually make this a vector. We make this a vector, and we call this the gradient of the function f. This is what's called the gradient. This is actually a collection of all the partial derivatives into a vector. And what the gradient is actually defined as is actually an operator like this is equal to all the partial derivatives are like partial f. I mean, we don't have partial f, though. We have it as an operator like partial x1, partial x1, and then partial x2, all the way up to partial xn, with n possible. There's n dimensions. Now we apply it to a function, and it will look like this. So now it's actually the operator on the function, so it will be partial f partial x1 and partial f partial x2. And we'll go up to partial f partial xn, right? This is how we operate it. So that's what we gotta do. And when we're here now, we've gotta actually compute it. So this is an example of how it is. And now let me go make this smaller because it's a little bit too big for us. We gotta go and work with things. So what is partial f partial x? 2x minus 4. That's it. So 2x minus 4, because this is y, that's constant, that's y, that's constant, that's nothing. Anyways, we already know that. So 2x minus 4, and what is partial and partial y? That's constant, 2y. And this is going to be minus 6. Okay, so that's what it is. Pretty simple, right? And now we can set those equal to 0 and see what it's going to be. The marker has a downside, which is this erasing, because it looks terrible when erased, but it's much easier to see, right? Okay, so now let's set these equal to 0. So let's say 2x minus 4 equals 0, and 2y minus 6 equals 0. We're going to set them equal to 0 to find the critical points, okay? So we can already tell this. We can rewrite it now. 2x equals to 4, 2y is equal to 6. So x equal to 4 over 2, and y is equal to 6 over 2. So x is equal to 2, and y is equal to 3. So this is the point 2, 3. And that's the domain now. Well, that's what we're going to put in to see that's the actual point. So we're going to see f of 2, 3 is equal to 2 squared plus 3 squared minus 4 times 2 minus 6 times 3 plus 13 equals to 4 plus 9 minus 8 minus 18 plus 13, which is equal to, this is going to be 13 minus 8, 5 minus 18 minus 13 plus 13 is equal to 0. And that's where the function is 0. So that's going to be, so the whole point is 2, 3, 0. This whole point. But now let's see. Let's use the Hessian matrix now to have all of the second derivatives instead of this gradient operator. We're going to use the Hessian. So I'll show you what that is. So 2, 3 is a max or a min. So we've got to find out max or minimum. So let's see. I'm sorry if this blue marker looks terrible, but this is what we have to work with right now. Look at how it looks. Whatever. Yeah, I know it looks bad, but what can we do? We don't have another marker that's better than this. So now, let's say we want, now we have partial, let's see the Hessian matrix, which is equal to, this is what we use for all of the second partial derivatives now. Mixed ones and non-mixed, which is equal to fxx, fxy, and we have fyx, and fyy. With respect to x, first partial derivative, with respect to y, first partial derivative, and then the columns will be second partial derivative x, second partial derivative y. That's just how they write it. And we already know the values. We don't even know the values yet, so we gotta find them. And I write it like this, but it really, if you like the other way, which is like this. And I'm just gonna write it so you understand. Also is, so we gotta find all of these, each and every one of them. And I don't really want to write down all of them like all at once, so let me go and just do it here. And we're gonna go and substitute it. So what is this? That's really you're gonna find the first one. That will be partial f, and partial x. And what is this? That's gonna be 2x minus 4. We find minus 4, and that's we're gonna find that. So it'll be partial x of with respect to y, 2y minus 4, and then partial y with respect to x will be the same thing here. 2x minus 4. You should understand this is just a partial y, a partial x. So partial y And now we're going to take this 2y minus 4. And now we're going to simplify this again. And we can just do it here in our heads. It's going to be 2. And we can see here, this is going to be 2. This is going to be 0. So that's going to be 0 actually, yeah. And we can see here, this is going to be 0 as well. You can see right here, this is going to be 2. And this is what we end up with 2. And like this, they write like the Hessian of that point at 2, 3. And that's what is equal to this. Right, too much space now. This is a square matrix to a 2 by 2 matrix. Write down 2 by 2 matrix. And this is a 0, now it's a 2. And now what we do is actually to take the determinants, so we know what happens around those points. And I'll explain them. That's like more complex things. I might talk about that later, but we're just going to understand this operation now. Determinant and the determinant of h. Now we're going to take the determinant, which is just multiplying these two and subtracting that with the multiplication of these two. So that will be 2 times 2 minus 0 times 0, which is equal to 4. And we got 4. And also because the determinant of h is greater than 0, that means we have a minimum. We found a minimum. This is how they do it, but I didn't want to like go too much into depth on this. I just wanted to show you this is one way they do it. They take the determinant and they call that a minimum. And it's hard to visualize it actually, though. Now we have all the tools and we have everything ready. We know partial derivatives and regular derivatives, and we know optimization, and we know about the negative log likelihood and about logistic regression and binary classification. We know a lot of things now, so now we can understand gradient descent at least a little bit, at least like a conceptual understanding what it is. So first, we have like an algorithm, and we remember what the gradient is, right? As an operator, the gradient is operator. Think of it as a collection of all of the partial derivatives, all the possible partial derivatives. And then the Hessian matrix has all of the second partial derivatives, all the possible ones. So Hessian matrix is 2 by 2 square matrix, and usually for 2 variables. So it just scales up when there's more variables. But when we have this, we have n variables. So it might be n by n. So now we know the gradients of the negative log likelihood, and we can write it like the log way. Or I should have shown this before, but you can also write a vector like this, containing all of the partial derivatives. I didn't really show it because it's not really used that much as notation, but we don't have that much space, so I'm just going to show it like this for now. It will be partial NLL, partial beta 1, and then we'll have partial NLL, partial beta 2, and then it will have partial NLL, partial beta 3, and then it's going to keep going until it reaches the last parameter, partial beta n. This is what it's going to be, and they write it like this with those type of things, those some arrows or something, whatever they're called, to just note that it's a vector. But I don't really write it like this because you don't know if it's a column vector or a row vector. But usually it's supposed to be a column vector, and all vectors are usually column vectors unless we define them differently. In machine learning, we think of it as column vectors. So it's supposed to be a column vector, but I wrote it like this because we don't have space to go vertically right now, because we have to do some things. We need this for beta, needed for optimizing the parameters, and needed for gradient descent, very important. And basically, the gradient descent algorithm is used to update the new parameters using the old parameters, and you can think of it as descending. So if you have a function like this, like one-dimensional, like a two-dimensional example, and I'm going to erase this later because we won't have space, but an example is like this parabola you see here, 2D example, and we know this is a minimum. This is our goal. We want to get to this with the negative log likelihood. We want to get to here with this gradient. So what we do is we go down, or we start here. Let's say we start there, and then we have a step, which is like, maybe the step is like this. The length of the step is the learning rate, which is called alpha, and this is the learning rate. Basically, the learning rate is how much we step. So this could be like the learning rate. This is how much we step, and we keep doing that, and we keep doing that, and we keep doing that, and we eventually get there. But what if this learning rate was larger? And we're starting at the same place, but now we can think about it. The learning rate is larger, and it went here now. This is alpha now, the new learning rate like that, and it maybe goes to here, and it maybe goes to here, and then we miss that. So this is the problem, we miss that, the minimum, when we have a larger learning rate. So we want to find the learning rate that is like in the right type of threshold. We have to have it in the right threshold, because then we might miss it. If we have it too slowly, if we have it, I'm thinking ahead again, but if we have it, if we have it like this, now let's think about if it was like this, if we started here and then we step this much as the alpha. So it would take a lot of them. It would take many dots to get to there. We would get to there, but it would take many dots, or that you can think of it as dots, but with many steps to get into the minimum. And it's going to stop at the minimum, and it tells, it's called like convergence, converging into the minimum. And that's how you can tell by like the previous gradient, the previous step minus, you would tell by the previous step, because right here, if you tell the step right here and here, you can see like the difference between the steps and see how close they are. Or of course we use partial derivatives for seeing the step. If we have a 3D example now with 3D, we would have something like this. Let's say it was very simple like that, and it's like this now. And now we would have the step like this. It is the same idea. You're like starting here, and we're like stepping. It's like a ball rolling down, and then it goes to the minimum right there. So it's like it's like stepping. It's called stepping. That's what gradient-descent. That's why it's descending. That's what it means, descending or stepping, whatever you can call it. And it comes from a recursive formula. You know the recursive formula is, well, let's use the beta parameters as our thing. We start at 1. We want to see the next beta variable. Beta I is equal to the next beta variable is equal to the previous variable, I minus 1 plus, minus, because we're descending, the common difference. You can think of it now as a sequence. That's like a sequence. In a sequence, it would be like that. The sequence of parameters. We have the next parameter will be equal to the previous parameter minus the common difference, or what we're descending by. I'll talk about that. But what we do instead of using I and I minus 1, then really that's the current parameter actually. This means the current parameter is equal to the previous one minus the common difference. So we find that if we want to find the current parameter, but we usually want to find the next one, which is a new one. New parameter is equal to the previous. I plus 1 is equal to the previous beta I minus the common difference. And what is the common difference? It has to be the learning rate, right? It has to be with the learning rate, and also we need the help of the partial derivative to actually go there. So that's why it's going to be alpha, which is the learning rate, times the gradient of the natural log likelihood, which consists of all the partial derivatives. So this is what it is. This is the gradient descent formula. We just have it right here. It wasn't that hard to derive it, right? It was very simple, right? It's not that hard to derive it. It's just this. That's it. And you should understand everything now after I explained it. This one is the new parameter. Is equal to the old parameter minus the common difference. It's really just the alpha, which is the learning rate and how much you're stepping by, times the gradient, which helps you actually go and step. So we want to find, let's first, well, before we even go into that, we want to find this. Well, remember, we want to find this, so we can see how each parameter contributes to this loss function, and then we can minimize that loss function with this. Remember that? And now, what is this equal to? Though first we got to refresh our memory on zi, and x, of course. We got to remember what zi is equal to. Is equal to beta naught plus beta 1 xi1 plus beta 2 xi2 plus beta 3 xi3, and you can keep going, but we're considering 3 data points. And remember that I is the data point, is actually the data point. So it can be 1 to 3, for example, when we had x as a matrix, as xi1, x11, x12, x13. Remember, these ones are all the data points, 2, 1, x2, 2, x2, 3, x3, 1, x3, 2, and x3, 3. And this was the height, this was the weight, and this was the blood pressure. Remember that? Because of the height is when the column has 1, that's the first column. So we see that here. We have the weight when it's in the second column, that's right there, and we have the we have the blood pressure when it's in the third column, and that's right there. But we just have different data points for each one. That's what the rows represent. So that's what I is the rows, or the, you can think of it as the rows if that's easy to remember, are data points. That helps me. So it's the data points. And remember what sigmoid of zi is. Sigmoid of zi is equal to 1 over 1 plus e to the negative zi. And you see here, this is, if you want to take the partial of this, it's going to be hard as well to do. You see that this is also inside of the function here, zi, and that's a function of beta 1. That's why we're going to multiply it by, by zi basically. So I can show you now. We know this is zi, and we know this is some sigmoid of zi. So let's get some space to write out the partial derivative of what it's going to be. And I'll talk about functions of functions of functions, because this is actually what the case is right now. It's a function of functions. Like, are like very ingrained, these chains of functions, chains of many functions together. That's why we use the chain rule, and I'll talk about this. So when we have this partial derivative of negative log likelihood with respect to any beta parameter, k, k number, or the number k, which is the index of the parameter, and remember I is the index of the data point. But we have here sigmoid of zi, and sigmoid of zi we already saw as a function of zi, and we already saw zi is also a function of our beta parameters. So it's like ingrained functions, chain functions. So that's why we're going to take the partial derivative of the negative log likelihood with respect to the sigmoid of zi first, because that is a function of zi which contains our beta parameters. And we're going to multiply that by partial derivative of the sigmoid of zi, and with respect to with respect to, we can't jump though into beta parameters because we have to see that zi is a function of that, because sigmoid of zi doesn't contain it. It does contain it basically if you think about zi, but you have to go inside of zi to actually see that. So that's going to be partial of zi, and we multiply that again by the partial root of zi. Now we're looking inside of zi, and we're actually taking the partial derivative with respect to the beta parameters. And you remember the chain rule, like this looks complex, so remember we had du dx times dy du. We can just cross these du's out, and that's equal to dy dx, right? You can see the same thing here. You can cross this out, cross that out, and you can cross those out. It's the same thing, except it looks like more stuff. Because we have a lot, our chain function is getting very confusing, and there's a lot of variables. That's why we have it like this now. And remember that first, if this is more, I'll try to explain it again. If everything flew over your head, we're seeing where you can think of it as looking at this function first, taking the partial derivative, and we're looking at this this variable, like with respect to this variable as our x value, for example, and that's our sigmoid of zi. And then we're multiplying it by inside of this function. We're seeing that, and we're seeing that zi. So then we can go and get to the beta parameters. Just think about it in terms of chain rule. If that didn't make sense either, chain rule is very important to understand. This is the chain rule. That's it. And now we can find this one will be very more tricky. It will be just tedious. This one will be easier. So we can do these two first, and let's try that out. So first, we can do partial zi and partial beta k. We already know that zi is just contains all of the, remember that zi equals to beta naught plus beta 1 xi1. I'm just gonna write it again, and this is gonna, you should write it as well to get it in your memory. xi2 plus beta 3 xi3, and any of these betas can be called beta k. And we see that we're taking respect to beta k. So if you look at one of them, let's say we're looking at this, for example, look at this one, for example, okay? Or we can look at that one either. We can also look at that. So let's look at this. It will be more intuitive. You see that this is like mx. So you just know m is the slope, right? And r1, our variable is beta 1, this is our constant. So now we're going to look at this. This is going to be our m. So now this is going to be equal to, well, it's going to be equal to xi, but it's going to change. It can be, we see these 2's and they share these 2's. This shares the 1 and this shares the 3, so it's going to be xik, and this is what it is. And if it's xi, it can be xi0, which is right here. There's nothing in there, so it's xi0 basically, or it's nothing. So now we know that partial zi with respect to beta k is just this, very easy, right? But now let's get to this one. Okay, so I cleaned up the space a little bit. So we have space, and I wrote this as xik because we already know this derivative evaluates to xik. We already found it out. It was very easy, right? Sigma, this is going to be the partial derivative with respect to zi of sigmoid of zi, which is 1 over 1 plus e to the negative zi. But I'm going to write it as 1 plus e to the negative zi to the negative 1 power. So it's going to be that. This is actually a fraction, but I don't want to see a fraction. So that's why I have the negative 1 power. So it's like the reciprocal. Think of it like that. So now we can use chain rule. And we can find first the derivative of e to the negative zi, which is going to be chain rule itself again, which is going to be negative. We see the derivative of negative zi, which is negative 1 times e to the negative zi. If we put a u there, it's just, which is going to be equal to negative e to the negative zi. Well, this is what the inside was. We took the derivative of the inside, which is negative e, negative zi, and we're going to multiply it with the outside derivative, which is another negative. So that's negative, and then we have, if we think of that as u as our substituted variable, it will be 1, it's going to be still u, which is 1 plus e to the negative zi, and then we're going to reduce the power because of the power rule, so it's going to be negative 2, and then we can write this now as, because of these negatives become positives, so it becomes e to the negative zi times 1 plus e to the negative zi squared. I just made it a fraction again. And now we can still simplify it, although it doesn't look like it could be simplified. We can actually use some tricks now to simplify it. So we have that right now, for now. But let's see how we can actually simplify that a little bit. So let me write it up here. E to the negative zi, 1 plus e to the negative zi squared. Okay? And now let's see, actually, remember what sigmoid was? Sigmoid of zi, it's 1 over 1 plus e to the negative zi, and 1 minus sigmoid of zi, this is some trick, I'll show you what it is, equals to, really 1 over 1, you can think of it as 1 plus e to the negative zi over 1 plus e to the negative zi, because they're the same variable, they're the same thing, so you can consider them crossing out, minus 1 over 1 plus e to the negative zi. Okay, so this is going to be crossing out, that's why I'm writing it like that. And you can see this 1 minus 1, so it's going to be, this is going to cross out with that, and it's just going to be this common denominator, so it's going to be equal to, oh no, we can't even write it yet, we have to still do, we have to do what this is equal to, which is e to the negative zi over 1 plus e to the negative zi. Okay, this is what we got. We can't be too excited yet because this is not everything. This is equal to 1 minus sigmoid of zi. And we can actually simplify this still. And we can do 1 plus e to the negative zi. It's getting kind of messy now. I'm sorry about that if it's like too hard to see. But we need this space there also. So then what we have this, and we can cancel this out. And now we found out e to the negative zi is equal to this whole thing here. Okay, and you might be thinking, why are we doing this, going through all this trouble? It's because if it's going to be very clean in the end, it will be very clean, you will like it. So this is what e to the negative zi is. And I'm going to simplify this a lot, so it doesn't look like this. It looks like, so e to the negative zi equals to 1 plus e to the negative zi times 1 minus sigmoid of zi. Okay, that's what it's equal to. We also know that 1 over sigmoid of zi, it's just 1 plus e to the negative zi, right? Yeah, I'm sorry if it looks like something weird, because of sigmoid of zi is equal to 1 over 1 plus e to the negative zi, and so it's going to be just the reciprocal, That's what it is. You can think of that is going to go to there. You can just you can multiply or whatever you do. It's just flipping them around, and we get this. So that's what we can have. We can substitute it with that, and if we substitute it with that, we can write it e to the negative zi as equal to 1 minus sigmoid of zi over sigmoid of zi. And this is what we got, okay? Because remember that this was 1 over sigmoid of zi, so we multiply them, this becomes in the denominator. So this is what we got. And we can substitute this with that e to the negative zi there. 1 minus sigmoid of zi divided by sigmoid of zi. And we have this whole thing. And we have this thing also, which is the same thing as 1 over sigmoid of zi. Remember that this is 1 over sigmoid of zi? I just showed you earlier. This is the same thing, 1 over sigmoid of zi squared, the whole thing. And this is what we have right now, and we got to multiply this out and do the algebra now. It's going to be 1 minus sigmoid of zi over sigmoid of zi times sigmoid of zi, we just do sigmoid of zi squared, because this reciprocal is going to become sigmoid of zi squared. And now we can cross this out with this, and that's going to be sigmoid of zi, so this power is going to become 1. And now that'll be 1 minus sigmoid of zi. And then we got to multiply that by sigmoid of zi. And this is what we got. This is what this is equal to. We just found it. It looks much cleaner than this, right? It looks much better. It's not a fraction anymore. So that's what this partial derivative evaluates to. And if you thought that was very like tedious, then wait for the next one. It's gonna be even worse. Sorry. Okay, so I wrote down these partial derivatives and I cleaned everything up. So we can actually have space to do the tedious one, which is I'm gonna have to maybe run a little bit smaller though, but even though it takes longer. Partial derivative. I think you won't see it that well though. That's the problem with it. So that's a little bit like medium sized. So let's see. So we want to do partial now of the negative log likelihood with respect to sigmoid of zi, right? So what is this going to be equal to? So really we're not doing too much chain rule. We are doing quite a lot though, still, but okay, let's see what this is going to be equal to. So let's go and write it out now. We can remember that the derivative of a sum is still a sum. So the summation doesn't affect the derivative. And this is going to be a negative there. It's not going to affect the derivative. And we know yi and 1 minus yi is not going to affect the derivative. The log is the most important thing that affects the derivative of a log. Okay, let's write it as a negative sum. And we're writing it as the whole thing. I equals to 1. And we're going to n. And then this is outside of the derivative. So let's go write the derivative inside. Because if it isn't, the derivative is not affected much by the sum. And so that's the partial derivative sigmoid of zi. And we have yi. I should have written that outside, it doesn't matter too much though. Log of sigmoid zi. And then we can add this with the next derivative of sigmoid zi with respect to sigmoid zi of 1 minus yi times log of 1 minus sigmoid of zi. Okay, and then this is what we're adding it with, and we're going to be down there. So let's do this one first. This is kind of yi is a constant, so we don't worry about that first. We can just keep yi there. Let me just write yi out. Yi is right here. We have it still, and we got to see the derivative of log x. Back to regular derivatives and have fun again. Log x. What is it going to be? This is just, we can just change the base. We can make it a derivative of natural log of x over natural log of 10, because this is a change of base. And we know natural log of 10 is a constant, so we can pull it to the front, 1 over natural log of 10. We know derivative of natural log of x is 1 over x, so it's going to be 1 over x times natural log of 10, so that's x natural log of 10 times that. So this is what it is. You don't even need my help, probably, because you're very good at this already, right? And now, that's what it is. That's log of x's, though. So now we got to see what is it for sigmoid of zi. And well, sigmoid of zi, for sigmoid, yes, sigmoid zi, yeah. It's going to be, we just replace the x with sigmoid zi. So it's going to be sigmoid zi natural log of 10. So this is what it is. That's what we got for the first one. Wow, yeah, we got it. Now that we can do the same thing for the next one, we just add it with this one, which is 1 minus yi, and we can just copy that with 1 minus, oh, now it will be a negative sign because of this minus, so the inside derivative will be a negative. And remember, we're taking it with respect to this, so it's going to be like treating as our x, for example, or what we're taking in respect to. That's why it's going to be negative. So negative, and then it's going to be 1 minus sigmoid of zi, and then we're going to multiply by natural log of 10, and that's what we got inside of this. Is that everything is inside of the summation, and we can go simplify this by factoring out the natural log of 10, and we get 1 natural log of 10 times yi over sigmoid of zi minus 1 minus yi over 1 minus sigmoid of zi. This is what we got, right? And now let's go add the summation to it. Summation right here. I equals to 1 to n. We'll make that negative, and we have this. This is what we got. We can't simplify that much, so I don't want to do any simplifying anymore, though. Anyways, this is what it is. Okay, we got this as our derivative for that, and remember, for basically, I didn't write it out anymore, but it's what we got. Okay, that's our derivative of the negative log likelihood with respect to sigmoid zi, and we multiply them by these. Remember what I just told you before? Just remember that. We multiply by these, so if we multiply these two, it's just going to be x like k times all of that. So we can move this negative to the front, and it will be x like k times sigmoid of zi. And I don't have space yet, so let me go. So you can, I'm moving the negative, so negative x like k times sigmoid of zi times 1 minus sigmoid of zi. We got that, and this is what, and we actually got our answer finally. This is a partial derivative of the negative log likelihood with respect to any beta parameter, k, and k index. This is it. This is what we have been waiting for so long. We finally got it. The partial derivative of the negative log likelihood with respect to any beta parameter is equal to this entire mess of terms, which is negative x like k times sigmoid of zi times 1 minus sigmoid of zi. If that's hard to read, let me go and adjust it. 1 minus sigmoid of zi times this whole bracket, which is contains the summation, and that's a sum of 1 over natural log of 10 times yi over sigmoid of zi minus 1 minus yi over 1 minus sigmoid of zi, and that's it. And remember what we were just doing. We're just using the chain rule. We're multiplying all of these with this derivative that we found here. This derivative, we're just multiplying all of these together, and that's what we get. And remember what we did here. We did some tricks to find this. This one was easy to find. We used some tricks for that, and we just used the derivative rules for this, a lot of chain rule. So now if you want to find the partial derivative of the negative log likelihood with respect to the first beta parameter, you can replace k with 1. You can also pick an index if you want as well, and then you can substitute it in, and you can do the adding, and you can have fun with that. Okay, but I'm not going to do that because this is enough for actually trying the math. This is what we're going to have to use in programming. Just this knowledge, this chain rule knowledge is what we need for programming. Very important. And also, don't forget what we're actually doing here. We're finding how, when we nudge these parameters, these beta parameters, when we change them, how does it affect loss function. Gradient of the negative log likelihood is what we're going to use for our gradient descent formula. Remember that beta 1, beta I, beta k, or new beta k plus 1 is equal to the beta k minus our common difference, which is just the learning rate times our gradient of the negative log likelihood. And we know the gradient of the negative log likelihood already, right? It's going to be just this. It's just this, but now it's inside of here, so it's just partial negative log likelihood, a partial beta 1, and then we have it more. This is, remember, this is a column vector. Partial negative log likelihood, partial beta 2, partial negative log likelihood, partial beta 3, and then we keep going into partial negative log likelihood, partial beta n. We ended there, and this is a lot of stuff, right? And this is what helps us get all of these parameters there. This whole expression here is what we use for classification. That's the partial derivative for actually gradient descent. And we use this in this formula, and we evaluate it, and we update the parameters, and we update them the correct way, and then we get the model to have the right. Remember what it's doing? Is making the beta parameters affect the input features in the right proportion, and when it affects in the right proportion, it can actually have the right output. And remember all of that, and come back to this video if you need more help or harder. So I'll see you guys later then. Thank you for watching the video, and I'll leave that up for now. I'm very proud of it.